Today we're doing some more Calculus 2 practice problems focusing on the trapezoidal rule and Simpson's rule for approximating integrals. So let's look at the trapezoidal rule. The trapezoidal rule is this right here, that if we have some function, we can find the area under a curve by doing an integral between the bounds of a and b of the function, right? But instead, with the trapezoidal rule, let's just take n amount of trapezoids. In this case, n is 4, right? Because we have 1, 2, 3, 4 trapezoids. And let's add up the areas of those trapezoids. And for this curve, you can see it's a very accurate estimation or approximation, right? But how does the trapezoidal rule, where does the formula come from? Well, what is the area of one of these trapezoids? So like this is trapezoid 1 and trapezoid 2. We can represent the first side length as f of 0 and the second side length as f of this first width. All these trapezoids have the same width if I drew them to scale correctly. They all have a delta x width. And what that comes out to be is delta x. It's the length of the entire region that we're looking at over the number of trapezoids, right? So in this case, delta x is just b minus a over n, right? The total distance across the bounds divided by the number of trapezoids. That would give the width of one trapezoid, right? So the formula for area of a trapezoid, this part right here, this 1/2, and you add up the two bases, that's just finding the average between the two bases. So that average comes out to be right here. So they're taking this length, which is 1/2 times the bases added together, right? It's their average, and multiplying by the width. So really when you're doing this formula right here, you're just finding the area of a rectangle, where the side length of that rectangle is, again, the average between this base and this base, right? So here's the area of one trapezoid. And what happens when the next one? Well, the only thing that changes is this base gets carried over to now the left side, right? These first two triangles share this base, right? So there's one on the left side, and then we move on to the next one, which is now at an x value of 2 delta x's away, right? That x value here is 2 delta x's. Okay, so we can add up all of these trapezoids. We can factor out the 1/2 and the delta x from all of them. That's going to leave us with, we have the first side length, and we have 2 of the second side length, right? 2 of the third, which is a 2 delta x, 2 of the fourth, which is a 3 delta x, and finally 1, I forgot my f, 1f of that last 4 delta x. So I can clear this up a bit. When we're adding up all of these bases, we have 1 here, I already noted the 2 here, and we have 2 here, 2 here, and then 1 here. This length right here is that f of 4 delta x, right? So you can see the pattern. Everything besides the first and last term has a coefficient of 2. And out front is that delta x over 2. The 2 comes from the 1/2 in front of all of them, and the delta x comes from multiplying by the height of the trapezoid. And remember, we could write that delta x as b minus a over n. I prefer to just leave it as delta x. So this is the formula we'll be working with. It's fairly easy to memorize once you understand what's happening. For Simpson's rule, we do something very similar. It's the same thing, right? We have this b minus a over n, which we're calling delta x. That's the width of any trapezoid. And instead of a 2, it turns to a 3. And instead of a 2, 2, and 2, for however many n's you have, it alternates between 4, 2, and 4, and n must be even so that the first term and the last term before the first and last terms will always start and end with a 4. So once you memorize the trapezoidal rule, this one will be easy. And you can set it up when you're doing the approximations to where all you have to do is change, again, this 2 to that 3, and change the coefficients of every other trapezoidal base length, right? So once we have these two memorized, we can look at actually doing some approximations. This says approximate the area under the curve using the trapezoidal and Simpson's rule, verify with a graphing utility. So we have this integral, right? And that would be a pretty tough integral to solve, but we can get a pretty good approximation of it quickly with the trapezoidal and Simpson's rule. So delta x, this is the width. I'm not going to bother drawing the region because you could draw it in your graphing calculator. We just have to pay attention that n is equal to 4. And we see that b equals 3 and a equals 1. So b minus a is 2 over n being 4. That just means that the width of these 4 rectangles is 1/2. And obviously 4 1/2 wide rectangles is a distance of 2. The distance of 2 between 1 and 3, right? So that just means that we have, I'll write out the formula again, delta x over 2, and we have f of 1 is our first, right? Because we're not starting at 0 anymore, we're starting at 1. Then we have 2f of 1 plus 1 width, right? So if we, I'm not going to draw the whole thing, but if we had something that kind of looks like this, right? This side length right here is f of 1. And remember, we have, when we calculate all the areas, we're going to count this length twice. So it's going to be 2, and it's going to be the function evaluated at 1 plus 1 width, right? Because we moved from 1 here to this, which is 1 plus 1 width, and the width was 0.5. So, and then we're going to do the same thing until we finally get to the last length, and we said that that length is just one of the functions evaluated, or one function evaluated at whatever a was, and now we have 4 delta x's, or that's just b, right? 1 and then 4 widths of those trapezoids. We're just ending up at 3 because 4 delta x is 2. So we're going to end at f of 3, right? So you see the pattern we're kind of working with. So with the trapezoidal rule, we said that delta x was 0.5 divided by 2. Now what you can do is you can save this function in your calculator and then call it up. Like you can, there's probably a variable button on your calculator, and you can find that function in that variable list. Like maybe you save the function as y1, and then you can call up that y1 function and evaluate it at different values very quickly, rather than typing out, 1 plus 1 over x plus 1 to the 5th plus 2 over 1 plus x to the now 1.25 to the 5th power. So it's a lot easier if you can use your calculator efficiently. But let's see, we'll have f of 1. We'll have 2 f's of 1.25. Again, that's the x value right here. We'll have 2 f's evaluated at 1.5. Wait, no, not 0.25. Delta x is 0.5. So it's going to be 1.5. This is x equals 1.5. And we have 2 of the function evaluated at 2. 2 of the function evaluated at 2.5. Finally, 1 of the function evaluated at 3. This is the trapezoidal rule. So you can punch all of this into your calculator. The answer that I got was 0.204. Okay, well, we don't know if that's accurate or not yet. We'll see at the end when we plug it into our integral capable calculator. But with Simpson's rule, the only thing that changes is, again, this 2 changes to a 3, and every other coefficient changes to a 4. So it's going to be 0.5 over 3 now, times f of 1 plus now 4f of 1.5 plus 2f of 2 plus now 4f of 2.5, and we're going to keep that f of 3. So obviously, by changing this to a 4 and this to a 4, this entire thing increased, right? We made that bigger, but we accounted for it by then, instead of dividing the function by 2, dividing by 3. So this, you can look up into how the Simpson's rule works, but we're just going to go off the formula. Plug all this into a calculator, and you would assume that it would be a little bit less if the function curves up, right? Because the approximation is better, so it's closer to the curve. Now we get 0.178, 0.178, okay? But when we actually plug it into the integral capability of the calculator, it looks like we just get 0.178, right? So, and there was some more decimals, this was just rounded, but they're pretty good approximations, right? Even the trapezoidal rule was not that far off. So that's how we use the trapezoidal rule and Simpson's rule to approximate this integral. Now let's look at another one. We have this function, square root of x times the square root of 1 minus x, and n equals 4, b equals 1, a equals 0. So let's figure out what the width of any given trapezoid is. It's going to be b minus a over n, or 1 over 4. So all of these trapezoids have a width of 1/4, and we're starting at 0. So the width, delta x, is 0.25 over 2. And we figured out how that 2 got there from the formula of the area. We're going to evaluate f. This is f, right? We're going to evaluate f at 0, and evaluate f twice at 0 and 1 width, and evaluate f twice at 2 widths, and evaluate f twice at 3 widths, and finally evaluate f once at that 4th width, or the b value of 1. So as you can see, we jumped by 0.25 each time because that is the width of our trapezoid. Okay, so plugging this into the calculator, just like that, yielded about 0.372, right? Oh, no, I read that wrong. 342. And with the Simpson's rule, what changes? Well, that 2 changes to a 3. We still have everything else except this coefficient and this coefficient will change to a 4. So now we have 4f of 0.25, 2f of 0.5, 4f of 0.75, and still that f of 1, right? And when we plug this into the calculator, we get about 0.372. Okay, getting closer. Finally, you can just plug the function into your calculator, and the value I got was 0.393. So this is the exact value. This was pretty close. This one was a little further off, but they're still pretty good approximations, right? So now let's look at error. Let's look at error with, well, yeah, that's how you do Simpson's rule and trapezoidal rule. But we have another application of error in this case. Error with the trapezoidal rule is given by this formula. We can see how far off we are. And if we're looking to get some certain error, then we can figure out how many trapezoids we should use. So it's a pretty useful skill. Let's see. If f of x is equal to x cubed, from 0 to 2, n equals 4. Let's plug this in to see what is the error. If you used only 4 trapezoids over this interval and going up to this function, how does that area compare to the actual area? So let's see. The absolute value of the error is going to be less than, what is b minus a? It is 2 cubed over 12 times n squared. What does this mean? This means take the second derivative and find the max on this interval. So this is kind of like Calc 1 refresher. But let's figure out what is f prime of x, right? So f prime of x is just 3x squared. F double prime of x is then 6x. So on the interval from 0 to 2, that's what this means. We're going, x has to be within 0 and 2. What is the maximum y value? Well, let's think about the graph of 6x. It looks kind of like this. This is 1. This is a y value of 6. This is 2. This is a y value of 12, right? It's just a line positively sloping. We can see that the maximum value occurs here at x equals 2. So we're going to plug in for all of this 12 because that is what the maximum value was, right? So all of that just turned to 12. Well, we can see at least that the 12 canceled the 12. And we can get rid of 2 squared on top and a 2 squared on the bottom. That's going to leave us with an error of about 2/4 or 0.5. Okay, so that is expected with 4 trapezoids. Let's also look at my other question. How large of n, meaning how many trapezoids should we use, would it take to get a very small 0.001 error? Okay, so that just means we'll plug that in for error. We'll plug that in. Errors 0, 0, 1. And we're just going to solve this for n. That's going to stay 8. That's going to stay 12. That's going to stay n squared. And that max is still going to stay 12. So the 12 and the 12 still cancel. And we are left with, well, let's solve it for n. We get n squared equals 8 over 0.001. This is obviously a big number. When you're dividing by such a small number, you're going to get a big number, which is expected because it would take a lot of trapezoids to get such little of an error. And n is the number of trapezoids. So n is going to be the square root of 8 over 0.001. Plug this into a calculator and you get 89.4 trapezoids. But we can't have 0.4 of a trapezoid, right? So we're just going to round up to 90 if we want that error to be less than or equal to. If we used 89, we wouldn't have enough. We would have like a 0.0. It would be bigger than 0.001. Just a little bit bigger, but still bigger. Okay, so I want to do the same question except with the error formula for Simpson's rule. And take a guess. Do you think for this question we're going to get a bigger or smaller number? I think it's going to be a smaller number and a much smaller number because we know that Simpson's rule is more accurate than the trapezoidal rule. So if it takes 90 trapezoids with that trapezoidal rule, it's definitely going to take less with Simpson's rule. So let's see, error. First of all, what is the error? Error, b minus a, we said was 2 to the 5th power over 180. N was 4, so we have 4 to the 4th power. What is the max? Well, we said that f double prime of x was 6x, so f triple prime of x is 6. And what is the 4th derivative? Derivative of 6 is 0. All that means is Simpson's rule is going to be so accurate in this case that there is literally 0 error because of the factors involved. Using 4 rectangles, we get an error of 0. Well, that probably means well, let's see. How large would n have to be to get a 0.001% error? Well, if it takes 4 rectangles to get 0, it's got to be less than 4. 3, 2, or 1. Let's see. We know that e is going to be less than or equal to, well, we know what e is. 0.001 is going to be less than or equal to 2 to the 5th power over 180 n to the fourth power times 0. So it doesn't even work because the Simpson's rule is already so accurate, right? So I would have liked to show that one. The point is that we can approximate error using these formulas, and they may or may not show up in your calculus lectures. Should we try? I want to try and do this with maybe a different kind of question. Imagine we change the function to x to the fourth power so that this error right here was no longer 0. If we change, let's do this again. If f of x is equal to x to the 4, then f prime of x is 4x cubed, f double prime of x is 12x squared, and f prime of x is 24x. That would be triple prime. Finally, the fourth derivative is a positive 24. So this would change to 2 to the fifth power over 180, 4 to the fourth power, now times 24. So now by changing the function, we actually do have an error now. Just plug this into your calculator. 2 to the fifth power times 24 divided by 180 times 4 to the fourth power. And I get a small error of 1 over 60, right? But it's not 0 now. So how many, if we get this small of an error, right, but that's not as small as 0.001, right? 1 over 60 as a decimal is 0.0166 repeating, right? So we can get that error smaller by introducing more rectangles. So let's see, if we want a 0.001% error, that's going to be less than or equal to 2 to the fifth power times 24 over 180 n to the fourth power. So solve this for n, you're going to, n is, we have 2 to the fifth power times 24 over 180 times 0.001. That's all to the 1/4 power. Just plug this into your calculator and you should get, let's see, 180 times 0.001, and we are going to raise this all to the 1/4 power to get 8 and some decimals after that, which means we want n to be 9. 8 rectangles is just too little to get that 0.001. Using 8 rectangles, the error is a little bit more than 0.001. So by using 9 rectangles, by using 5 more rectangles, we're able to change the error. Again, this was equal to 0.016 repeating. By using 5 more rectangles, we're able to decrease that error to 0.001. So that's just a neat little application of error with the trapezoidal and Simpson's rule, but you may or may not be tested on that. Some professors do like to test on that. This is what's more important, though, is using the actual formulas. So that is how you do Simpson's rule and trapezoidal rule.